Something is wrong with your suit. You're floating. Not gently, the way you imagined it as a kid lying in the backyard at night and staring up. You're floating the way a leaf floats above a fire, weightless and helpless and entirely at the mercy of something that does not care whether you live or die. And right now, 340 miles above the surface of Earth, with nothing between you and the absolute black, nothing of space except a few millimeters of reinforced fabric, you are starting to understand something the textbooks never quite conveyed. Space does not want to kill you. That's the part nobody tells you. It doesn't want anything. It is simply a place where everything that keeps you alive stops working, and it has been that way for 14 billion years before you arrived, and it will be that way for trillions of years after you are gone. The question we're here to answer today is not whether space can kill you. That part is settled. The question is how far you could actually get before it does. And the answer is one of the most quietly unnerving things I have ever sat down and thought through. Because it's not just a story about distance. It's a story about what distance means when every kilometer you travel away from this pale blue dot is another step into a universe that is older and emptier and stranger than anything your nervous system was ever built to comprehend. We're going to travel today, you and I, together. We're going to start on the moon, which is already far enough to ruin everything, and we are going to keep going. Past Mars, past Jupiter, past the edge of the solar system, past the nearest stars, across the Milky Way, through the local group of galaxies, and all the way to the absolute edge of the observable universe. And at every stop, I want you to understand not just what kills you, but what it actually feels like to be there. What the light looks like. What the silence sounds like. What it means to be a human body in a place that has no concept of human bodies. Here is the thing about you specifically. Every atom you are made of was forged inside a star. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now as you read this, every single one of those atoms was cooked inside a stellar furnace billions of years ago and then scattered across the galaxy when that star exploded. You are, in the most literal sense that chemistry allows, made of the universe. And today we're going to find out how far back into that universe you could actually travel before the universe takes you apart. This isn't a thought experiment about astronauts or rocket ships. This is about you, your body, your cells, your fragile and extraordinary human life, and the places in this cosmos where that life simply cannot continue. NASA's data, the research from the International Space Station, the findings from every deep space mission we've ever launched, all of it points to the same conclusion. The universe is not a place we were designed for. And the further you go, the more violently true that becomes. But here's what nobody talks about when they talk about space travel. It's not the cold that gets you first. It's not the vacuum. It's not even the loneliness, though that one is genuinely terrifying in ways we'll get to. It's the radiation. And there's something about radiation that changes everything, because unlike a wall or a cliff or a temperature you can feel, radiation is invisible. It is passing through you right now, just sitting where you are. Cosmic rays from distant supernovae, gamma rays from the galactic center, solar particles from our own sun, they are moving through your body at this very moment, and your body handles it because the Earth's magnetic field and atmosphere absorb most of the damage. The moment you leave, that protection is gone. And the moment it's gone, the clock starts ticking. So let's start at the first destination. The one that feels close enough to touch on a clear night when you look up and see it hanging there, full and white and impossibly near. Chapter 1. The Moon. The Moon is 384,400 kilometers away from Earth. That sounds like a lot until I put it this way. If you could drive there in a car at highway speed, never stopping, never sleeping, the trip would take roughly 150 days. That's about the same amount of time it takes a human embryo to go from a cluster of cells to a fully formed fetus that can hear sound. That's how far the moon is. Not incomprehensibly distant, just far enough that everything changes. The first thing that would try to kill you on the moon has no color and no texture, and you cannot feel it arriving. During a solar storm, the radiation dose on the lunar surface can reach 50 millisieverts per hour. To understand what that means to your body, consider this. The recommended safe limit for radiation workers, the people who work in nuclear power plants and radiology departments, the people who have decided to spend their careers near radioactive material, is 20 millisieverts per year. On the moon during a solar event, you would absorb that annual limit in 24 minutes. An hour of unshielded exposure during a major solar flare would leave you with a radiation dose that dramatically increases your lifetime cancer risk and begins to damage your bone marrow. 6 hours of it, and you would start experiencing acute radiation syndrome. Nausea first. Then your immune system begins to fail. Then, depending on the dose, things get significantly worse. But let's say you have a shelter. Let's say you have a lunar habitat with walls thick enough to absorb most of the solar radiation. The moon still has problems that shelter alone cannot solve. The temperature on the lunar surface swings from 127 degrees Celsius at midday in sunlight to minus 173 degrees Celsius during the lunar night. That's a temperature range of 300 degrees between the same two spots on the same surface separated by 2 weeks of time. To give that swing a human anchor point, it's the difference between touching a pan fresh off the stove and placing your hand inside a freezer set as cold as it will go, then multiplying that difference by 6 and applying it to an entire landscape. No atmosphere means that heat doesn't distribute. There's no air to carry warmth from the sunny side to the dark side. It is either one extreme or the other, and there is nothing in between. And then there are the micrometeorites. The moon has no atmosphere to burn up the constant rain of tiny space debris that the solar system is always throwing around. On Earth, these fragments burn up high above you, producing those brief streaks of light you call shooting stars. On the moon, they arrive at the surface at velocities that can exceed 70 kilometers per second. At that speed, a fragment smaller than a grain of rice carries the kinetic energy of a small bullet. The lunar surface is constantly being sandblasted by these particles, and any equipment, suit, or structure left on the moon for extended periods begins to degrade. The Apollo spacesuits, which were designed and tested here on Earth, degraded noticeably in just the few days the astronauts spent on the surface. The abrasive lunar dust, which is jagged in ways that terrestrial dust is not because it has never been smoothed by wind or water, worked its way into every seal and joint and mechanism. The astronauts came back with suits that smelled, as they described it, like gunpowder. But let's say you solve all of that. Let's say you have a suit that handles the temperature and the radiation and the micrometeorites. You still have the dust problem. Lunar dust is not like beach sand. It's made of sharp, glassy particles created by billions of years of micrometeorite impacts, and it carries an electrostatic charge that makes it cling to everything. It clogs air filters. It scratches helmet visors. It damages the seals on airlocks. And when it gets inside a habitat, it becomes a health hazard because those sharp particles, when inhaled, lacerate lung tissue in ways that are not reversible. During the Apollo missions, astronaut Harrison Schmitt developed symptoms described as lunar dust hay fever within hours of being exposed to dust that had tracked into the lunar module. His eyes ran. His sinuses swelled. His throat felt raw. This was a few grams of dust briefly. Imagine a year. Still, you could survive on the moon. With the right technology, the right infrastructure, the right supply chain from Earth, the moon is survivable. It is difficult and expensive and dangerous, but it is within the reach of human ingenuity. The moon is, if you tilt your head and look at it charitably, a neighborhood problem. The next destination is something else entirely. Chapter 2: Mars. Mars sits at an average distance of about 225 million kilometers from Earth. That number is so large it tends to bounce off the brain without leaving a mark, so let me make it physical. If every kilometer of that distance were 1 millimeter on a piece of paper, the paper would need to be 225 kilometers long. That's roughly the length of the English Channel. You'd need to lay a piece of paper from London to Paris just to represent the average distance from Earth to Mars at millimeter scale. And depending on where Mars and Earth are in their orbits, the actual distance can swing from about 54 million kilometers when we're closest to about 401 million kilometers when we're on opposite sides of the Sun. The journey itself, using current rocket technology and the most efficient orbital paths, takes between 6 and 9 months. And every second of that journey, you are being cooked. In interplanetary space between Earth and Mars, you are exposed to two types of radiation that should be thought of as completely separate threats. The first is solar particle events, bursts of energetic protons that the Sun throws out during solar flares and coronal mass ejections. The second is galactic cosmic rays, high-energy particles that come from outside the solar system, from supernovae and other violent events in the galaxy, and which are genuinely difficult to stop because they move at close to the speed of light and can punch through most shielding material. The research done using data from NASA's Curiosity rover during its trip to Mars found that the radiation exposure during a 180-day journey was approximately 300 millisieverts. Remember, the annual limit for nuclear workers is 20 millisieverts. The trip to Mars would expose you to 15 times that recommended annual limit before you even arrived. And then you'd need to spend time on Mars. And then you'd need to travel home. NASA has calculated that a round trip to Mars, 6 months there, a year and a half on the surface waiting for the planetary alignment to make the return trip possible, and 6 months back, would expose an astronaut to a total radiation dose that increases their lifetime cancer risk by approximately 5%. That sounds manageable until you think about what that means across a crew of 10 people. Statistically, in every group of 10 people who make that trip, one of them will develop cancer as a direct result of the journey that would not otherwise have developed. The radiation doesn't feel like anything. You wouldn't know it was happening. You'd be floating in your spacecraft, watching movies, eating rehydrated food, doing exercises to keep your muscles from atrophying in zero gravity. And the whole time, silently, like rust forming on metal in a damp room, the radiation would be accumulating in your cells, breaking DNA strands, causing mutations that would take years or decades to manifest. And Mars itself, when you arrive, is not the hospitable, rust-colored destination the science fiction films have made it look. The average temperature on Mars is minus 63 degrees Celsius. That's colder than the coldest temperature ever recorded on the surface of Earth, which happened at a Soviet research station in Antarctica in 1983. And even that temperature, minus 89 degrees Celsius, would be what passes for a mild day by Martian standards in certain regions. At night near the poles, Martian temperatures drop to minus 125 degrees Celsius. This is colder than the boiling point of oxygen, which means that on a cold Martian night, oxygen itself would condense out of the atmosphere if there were enough of it, which there isn't. The Martian atmosphere is about 95% carbon dioxide, with an atmospheric pressure equal to roughly 1% of Earth's. Standing on the Martian surface without a spacesuit would not leave you time to appreciate how thin the atmosphere is, because the lack of air pressure would cause your blood to begin to vaporize in less than a minute. Your saliva would boil. The fluids in your eyes would expand. You would lose consciousness in about 15 seconds, and the damage to your cardiovascular system would be irreversible within minutes. The thin atmosphere also means almost no protection from ultraviolet radiation from the sun, which on Mars arrives at the surface with an intensity that would cause severe sunburn in minutes on exposed skin. Then there are the dust storms. Martian dust storms are not the dramatic, swirling walls of sand depicted in films where they have the structural integrity of a physical barrier. The atmosphere is so thin that even in the most intense dust storm, the wind pressure on a human body would feel like a gentle breeze by Earth standards. But the dust itself is a problem. It's perchlorates, highly reactive chemical compounds that are toxic to the human thyroid and which, when inhaled, interfere with the production of thyroid hormones. If Martian dust got into a habitat and someone breathed enough of it, the health consequences over months and years would be significant. And the dust storms can last for months. In 2018, a global dust storm on Mars that lasted for over 3 months covered the entire planet in a layer of atmospheric dust that reduced sunlight to the surface by nearly 99%. The kind of darkness that falls over an entire world. But here is the genuinely painful part about Mars. Of all the places we're going to visit today, Mars is the only one where, with extraordinary effort and enormous resources and generations of engineering, survival might actually be possible. We could imagine pressurized habitats. We could imagine greenhouses with LED grow lights. We could imagine life on Mars, albeit a life more constrained and difficult than anything a human has ever lived. After Mars, every destination we visit is not a matter of better technology. It's a matter of physics. And physics has opinions. Chapter 3: The Asteroid Belt and Jupiter. Between Mars and Jupiter lies the asteroid belt, and the asteroid belt is one of the great disappointments of the solar system if you're expecting something dramatic. Science fiction has given us the image of a dense field of tumbling rocks so tightly packed that a spacecraft must thread its way through them like a needle through a crowded room. The reality is almost disappointingly vast and empty. The asteroid belt spans an enormous region of space, and if you took every single asteroid in it and pressed them all together, the total mass would be less than 4% of the mass of our moon. That entire sea of rocks, if you scooped it all up, would be smaller than an object already sitting up there in the night sky, visible to the naked eye. The average distance between asteroids is roughly 970,000 kilometers. That's about 2.5 times the distance from Earth to the Moon. You could sail through the asteroid belt, and statistically, the odds of hitting anything large enough to matter are extremely small. Every robotic spacecraft we've ever sent past it has done so without incident. But the asteroid belt is not what kills you on this leg of the journey. What kills you is the gradual accumulation of everything we've already discussed, the radiation dose building quietly in your cells, the effect of long-duration zero gravity on your bones and muscles, the psychological weight of being further from Earth than any human has ever been. By the time you're crossing the asteroid belt, you are so far from home that a radio signal traveling at the speed of light, the fastest speed anything in the universe can move, takes about 20 to 40 minutes to reach Earth. When Mission Control speaks to you, you wait. You wait 20 minutes for the signal to arrive. You send your reply, and then you wait another 20 minutes for their response. A simple conversation takes nearly an hour. And there is something about that delay that is not just an inconvenience but a fundamental redefinition of what it means to be connected to the rest of humanity. You are no longer in the conversation. You are separated from it by the speed of light, which cannot be negotiated with. Jupiter is 778 million kilometers from the Sun, and it represents the first destination where your survival problem is no longer primarily about radiation or cold or thin atmosphere. It's about something more fundamental. Jupiter doesn't have a surface. When people imagine visiting Jupiter, there's often the implicit assumption that you would land somewhere. But Jupiter is a gas giant, and it's made almost entirely of hydrogen and helium gas compressed by gravity into something that gradually gets denser and hotter as you descend into it, transitioning from gas to liquid to something that behaves like a metallic fluid, all the way down to a core that may be solid, and where temperatures reach around 24,000 degrees Celsius. Hotter than the surface of the sun. There is nowhere to stand. But let's say you approach Jupiter without descending into it. Even in orbit or on approach, Jupiter's radiation environment is one of the most hostile places in the entire solar system. Jupiter has an enormous magnetic field, about 20,000 times stronger than Earth's, and that field traps charged particles from the sun and from the solar wind into radiation belts that encircle the planet. These radiation belts are so intense that a person in a standard spacesuit, exposed to them without additional shielding, would receive a fatal radiation dose within hours. The Galileo spacecraft, the robotic probe NASA sent to study Jupiter in the 1990s, was specifically engineered with heavy radiation shielding for its electronics, and even then, the radiation environment slowly degraded its instruments over the years of its mission. If you were a human being in that environment without extraordinary protection, the radiation dose would be roughly equivalent to receiving 10 to 11 head CT scans every hour indefinitely. That's not a precise enough comparison. Let me make it starker. The radiation environment in the most intense part of Jupiter's radiation belts is about 3.6 million Röntgen per hour. A dose of 500 Röntgen is enough to kill a person. That means the most intense Jovian radiation zones would kill you in roughly 8 seconds. Chapter 4. The Outer Solar System. Beyond Jupiter, the solar system becomes a different kind of place. Saturn sits at a distance of about 1.4 billion kilometers from the Sun. If you were to shrink the distance from the Earth to the Sun to the length of a single page in a standard novel, the distance to Saturn would stretch for about 14.5 pages. Uranus is at 29 pages. Neptune, the furthest true planet, is at 45 pages. And the solar system, in its full extent, goes on for roughly 1,000 more pages after that. We live in the first sentence of a very long book. At Saturn, the cold becomes something different than it was on Mars. The cloud tops of Saturn are around minus 178 degrees Celsius. But it's not the temperature that defines the experience of being near Saturn, it's the light. At Saturn's distance from the Sun, sunlight arrives at roughly 1% of the intensity it has on Earth. The Sun, from Saturn, would look like a very bright star. Not the warm, overwhelming disk, you know, just the brightest star in a sky full of stars. There would still be enough light to see by. The rings of Saturn, those billions of chunks of ice and rock ranging in size from a grain of dust to the size of a house, would catch that faint sunlight and scatter it, and Saturn itself would be surrounded by this extraordinary halo of reflected light. But you would feel none of its warmth. The cold would be absolute and complete. Uranus, at nearly 2.9 billion kilometers from the Sun, is a world that spins on its side. Its axial tilt is 98 degrees, meaning its poles point almost directly at the Sun for decades at a time, and then spend decades in complete darkness. The northern pole of Uranus spent 42 years in total darkness before emerging into 42 years of continuous sunlight. The ice giant's atmosphere is made primarily of hydrogen and helium, with significant amounts of methane, and it is the methane that gives it the pale blue-green color you see in photographs. The temperatures at Uranus's cloud tops hover around minus 224 degrees Celsius, making it the coldest planetary atmosphere in the solar system despite Neptune being further from the Sun. At Uranus, whatever heat remains inside the planet from its formation has somehow been trapped, and very little escapes. It is a cold world in the deepest sense of that word. Neptune is the last planet, 4.5 billion kilometers from the Sun. At that distance, sunlight takes over 4 hours to arrive. If the Sun somehow disappeared at this exact moment, Neptune would not notice for 4.5 hours. The winds on Neptune are the fastest of any planet we know of, reaching speeds of 2,100 kilometers per hour. To understand what that wind speed means, Think about the fastest commercial airliner you've ever flown on. That aircraft, traveling at its cruising speed, would be blown backwards by Neptune's winds. And those winds circle the entire planet. There is no shelter. There is no eye. The storm is the entire world. After Neptune comes Pluto, demoted to dwarf planet but still real and still remarkable. At 5.9 billion kilometers from the Sun on average, Pluto's surface temperature is around -230 degrees Celsius. At that temperature, nitrogen freezes. Nitrogen, the gas that makes up 78% of the air you are breathing right now, would condense on Pluto's surface into a solid. You could theoretically walk on plains of frozen nitrogen. The light from the Sun at Pluto's distance would be so dim that midday on Pluto would look roughly like twilight on Earth. Not quite night, but never quite day. A permanent gentle dusk covering an entire world. There is something about that image that stays with me. A whole planet caught in the moment between light and darkness, forever, for billions of years. Chapter 5. The Edge of the Solar System. But Pluto is not the edge of the solar system. Not even close. The solar system doesn't end with the planets at all. It extends through the Kuiper Belt, a vast disk of icy bodies extending from Neptune's orbit out to about 50 astronomical units from the Sun. An astronomical unit is the distance from the Earth to the Sun, about 150 million kilometers. 50 astronomical units is about 7.5 billion kilometers. And even beyond the Kuiper Belt, the Sun's influence continues in the form of the heliosphere. The heliosphere is the enormous bubble created by the solar wind, the constant stream of charged particles that flows outward from the Sun in all directions. This bubble extends to somewhere between 100 and 150 astronomical units from the Sun. And the edge of that bubble, the point where the solar wind finally loses the battle against the interstellar medium and slows to a stop, is called the heliopause. We know the heliopause exists because we have sent something there. Voyager 1, launched by NASA in September of 1977, crossed the heliopause in August of 2012 and became the first human-made object to enter interstellar space. As of today, Voyager 1 is roughly 23 billion kilometers from the Sun. To make that number feel real in your body, imagine laying a tape measure from New York to Los Angeles. That distance, coast to coast across the continental United States, is about 4,500 kilometers. Voyager 1's distance from the Sun is equivalent to laying that same tape measure more than 5 million times end to end. And it's still in our cosmic neighborhood. At the heliopause and beyond, several things happen to a human body simultaneously, and all of them are bad. First, the Sun's magnetic field, which has been deflecting some of the most energetic galactic cosmic rays from reaching you throughout the inner solar system, weakens dramatically. In the heliosphere, you have some protection from galactic cosmic rays because the Sun's extended magnetic field bends the paths of some of these particles. Cross the heliopause and that protection is gone. The galactic cosmic ray flux in interstellar space is significantly higher than inside the heliosphere. These are not the kind of radiation you can easily shield against. A 1 centimeter thick aluminium wall, the kind that makes up much of a spacecraft's structure, barely slows these particles. You would need meters of dense material to meaningfully reduce the dose, and carrying that much shielding makes a spacecraft so heavy it becomes nearly impossible to launch with conventional technology. Second, at the heliopause, the temperature of the surrounding medium drops towards something close to the background temperature of the universe itself. Deep interstellar space has a temperature of approximately 2.7 Kelvin, which is 2.7 degrees above absolute zero, the coldest temperature that physics allows. Absolute zero is minus 273.15 degrees Celsius. At 2.7 Kelvin, you are 270.45 degrees below the freezing point of water. There is no heat anywhere in this direction. The only warmth in the universe, the warmth that still lingers from the Big Bang as a faint glow of microwave radiation, reduces to this thin whisper of temperature. If you could somehow stand in interstellar space without a suit, the cold would be so complete that every molecular process in your body would stop almost instantly. Not slowly, the way freezing on Earth is slow. Instantly. Because there is nothing out there to transfer heat away from you gradually. The vacuum itself simply has no molecules to carry anything. You would become frozen so rapidly that the experience would not even register as cold. Third, the complete absence of the sun's charged particles means that you lose the last faint reminder that a star exists. Inside the heliosphere, even at Pluto's distance, the solar wind still blows past you. You can detect it. You are still, in a real physical sense, inside the sun's extended atmosphere. Cross the heliopause, and you are in a genuinely different place. A place that has never known the sun. A place that the light of our star reaches only as a point, the same as any other star. And for a human being whose entire biology and psychology and cultural history has been calibrated to the rhythms of one particular star, arriving in a place where that star becomes just another light in the sky is not just a logistical problem. It is something else. Something that I think would register in the bones before it registered in the mind. Chapter 6. The space between stars. The nearest star system to our Sun is Alpha Centauri, a triple star system located about 4.24 light-years away, if we count Proxima Centauri, the small red dwarf that is the closest of the three. A light-year is the distance light travels in 1 year, and light travels at 299,792 kilometers per second. In 1 second, light travels roughly the distance you would need to drive around the entire Earth 7.5 times. In 1 year, light travels about 9.46 trillion kilometers. 4.24 light-years is therefore about 40 trillion kilometers. 40,000 billion kilometers. If you drove there in a car at highway speed without stopping, the journey would take you approximately 48 million years. The dinosaurs went extinct 66 million years ago. You would need to start your trip when ankylosaurs were still alive, and non-avian dinosaurs still ruled the land, and arrive with time left over before the impact. Our fastest spacecraft, Voyager 1, is currently traveling at about 17 kilometers per second. At that speed, it would take Voyager 1 roughly 73,000 years to reach Alpha Centauri if it were heading in that direction, which it isn't. 73,000 years. To put that in context, modern humans, Homo sapiens with essentially our current anatomy and brain capacity, have only been around for about 300,000 years. And we've only had anything resembling civilization for perhaps 12,000 years. At our current fastest speed, reaching the nearest star would take 6 times the entire span of recorded human history. But let's say we solved the propulsion problem. Let's say we built a spacecraft that could travel at, say, 10% of the speed of light. That's incredibly fast by any measure. The fastest human-made object we've ever created was the Parker Solar Probe, which reached about 690,000 kilometers per hour, or about 0.064% of the speed of light. Getting to 10% of light speed would require a revolution in physics and engineering that we cannot currently envision. But let's grant it. At 10% of light speed, the trip to Alpha Centauri would take about 42 years. A human lifetime, roughly. Someone born on the ship might live to see the destination. What happens to a human body during 42 years of interstellar travel is one of the most sobering thought experiments in all of space medicine. The first problem is the same one we've been tracking since we left Earth. Radiation. In interstellar space, protected by nothing, receiving the full unfiltered flux of galactic cosmic rays, the radiation dose accumulates over years the way interest compounds in a bank account you can't close. High-energy cosmic rays damage DNA. They create secondary particles when they hit material, and those secondary particles cause their own damage. Research suggests that after prolonged exposure, they are particularly harmful to cognitive function, damaging neurons in the hippocampus, the part of the brain that handles memory and spatial navigation, and in the frontal lobe, which governs decision-making and impulse control. A crew of astronauts who spent 42 years in interstellar space might arrive at Alpha Centauri with measurably impaired cognitive function, reduced memory capacity, and altered personalities. They would not be the same people who left. And here we reach something that the science alone cannot quite capture. The psychological weight of interstellar space is not just about confinement or boredom or the absence of nature, though all of those things are real and documented in the research done on long-duration missions and isolation studies. It's about something more specific to where you are. On a Mars mission, you are still in the solar system. Earth is a visible dot. You can find the sun in the sky with your eyes. You know where you are in a cosmological sense. The universe has landmarks. But in interstellar space, between the stars, there are no landmarks. There are just stars in every direction, none of them close, none of them the particular star you belong to. The sun would be visible to the naked eye until you were a few light years out. Then it would begin to fade. And at some point, it would fall below the threshold of naked eye visibility. You would no longer be able to see the star you come from without a telescope. That moment, I think, would be one of the loneliest things a human being has ever experienced. Not metaphorically, physically. The light from your home, extinguished from your personal sky. The interstellar medium, the thin gas and dust that fills the space between stars, is not a complete vacuum. There is roughly 1 atom of hydrogen per cubic centimeter in the interstellar medium. That sounds like almost nothing, and it is almost nothing. But at 10% of the speed of light, those atoms would hit the spacecraft's hull with enormous kinetic energy. Each individual impact is minuscule, but at that speed, the cumulative effect would begin to erode the hull. Every second of travel at that speed, every square meter of the forward-facing surface of the spacecraft would be struck by billions of those atoms. Over 42 years, the erosion would be significant. The ship would need a thick forward shield, something that could absorb this constant bombardment over decades, and that shield would need to be replaced or regenerated periodically, which is an engineering challenge we have not yet solved. Chapter 7. What kills you in interstellar space? Let's pause here and think honestly about what we're dealing with. Because at this point in the journey, we've left behind all the familiar risks. We're not worried about running out of oxygen in a failed habitat, not thinking about dust storms on Mars, not calculating radiation belts around Jupiter. The risks at this scale are quieter and stranger. They are the risks of isolation, of time, of the relentless nature of physics. The human body was shaped by evolution to live on one specific planet. Not just to survive on it, but to thrive on it. The gravity, the atmospheric pressure, the spectrum of sunlight, the rhythm of day and night, the presence of other humans, all of these things are not incidental. They are the environment that your biology assumes it will have, and when it doesn't have them, it begins to fail in specific and documented ways. Zero gravity causes bone density loss. In microgravity, the mechanical stress that normally forces your bones to maintain their density disappears. Astronauts on the International Space Station, after 6 months in orbit, have lost an average of about 1 to 2% of their bone density per month. That might sound small until you realize that a year and a half at that rate would leave your bones with the density of an elderly person who has spent decades developing osteoporosis. Current exercise regimens on the space station can reduce this loss but not eliminate it. On a 42-year interstellar journey, even with the best possible exercise protocols, the skeletal changes would be profound. If the crew somehow arrived at Alpha Centauri after 42 years in zero gravity and attempted to land on a planet with Earth-like gravity, the physical shock to their bodies might be fatal. Their hearts, which would have atrophied from not having to pump blood against gravity, would struggle to function. Their bones might fracture under their own weight. Their muscles would have wasted even with exercise because no amount of exercise in zero gravity perfectly replicates the constant mechanical load of standing on a solid surface. Vision problems too. Studies of astronauts returning from long-duration missions on the space station have found that many develop a condition called spaceflight-associated neuroocular syndrome. Without gravity pulling fluids downward, body fluids redistribute toward the head. This increases intracranial pressure, which presses on the backs of the eyes and can flatten them, changing their shape and damaging the optic nerve. The result can be permanent vision impairment. Something like 60% of astronauts on long-duration missions report some degree of visual change. On a 42-year mission in zero gravity, the cumulative effect on eyesight could be severe. Sleep is disrupted in space. The human circadian rhythm evolved in response to the 24-hour cycle of light and dark on Earth. In space, with no natural light cycles and no environmental cues, sleep patterns fragment. On the space station, where they orbit the Earth every 90 minutes and experience 16 sunrises and sunsets per day, astronauts follow an artificial schedule. But in interstellar space, even that stimulus would be absent. The stars don't rise and set. There is no horizon. There is just the constant dark of space and the unchanging light of the distant stars and the electric lights of the spacecraft. Chronic sleep disruption over years has cascading effects on cognitive function, immune response, metabolic health, and emotional regulation. And then there is the loneliness itself, which is not just a mood, but a biological state. Humans evolved as social animals. Our nervous systems are calibrated to the presence of other humans. Touch, conversation, shared space, the unconscious reading of facial expressions and body language, all of these things regulate our stress hormones, our immune function, our sense of self. In the isolated, confined environment of an interstellar spacecraft, with a crew small enough to count on two hands and nowhere else to go, the social dynamics would become everything. Research on isolated groups, whether in Antarctic stations or submarine crews or psychology experiments, consistently shows that after months of intense isolation, even people who genuinely like each other begin to develop tensions that can become serious. Interpersonal conflicts in a space this confined, with no exit and no outside perspective, would require extraordinary psychological resilience from everyone involved. Chapter 8: Proxima Centauri and the Nearest Stars. If we somehow arrived at Proxima Centauri, the nearest individual star to our Sun, what would we find? Proxima Centauri is a red dwarf star, small and dim and ancient. It has about 12% of the Sun's mass and about 14% of its diameter. From the surface of a planet orbiting it, it would look larger than our Sun looks from Earth, because the habitable zone, the distance range where liquid water could exist, is much closer to a red dwarf than to a star like ours. Proxima Centauri b, a planet that appears to orbit within this habitable zone, completes an orbit in just 11.2 days. It is so close to its star that it is very likely tidally locked, meaning one side always faces the star and the other side always faces away, like how the moon always shows us the same face. On the star-facing side, it would be perpetually scorching, the stellar radiation arriving with relentless intensity. On the dark side, it would be in permanent night, colder than anything on Earth. Between them, at the terminator line where day meets night, there might theoretically be a narrow band of moderate temperatures. But there is another problem. Proxima Centauri is a flare star. It erupts with enormous stellar flares, bursts of X-ray and ultraviolet radiation that can increase its overall brightness by as much as 8 times within seconds. Because the habitable zone is so close to the star, any planet there would be bathed in these flares with almost no warning. Research published in 2021 found evidence of a massive superflare from Proxima Centauri that would have been 100 times more energetic than the strongest flares from our own sun. Such events would strip away planetary atmospheres over geological time, and any surface life would need extraordinary shielding to survive, which, biologically speaking, we don't have. The nearest stars are humbling in a particular way. We have been looking at the light of Proxima Centauri for as long as humans have had eyes capable of seeing stars. That light left its source 4.24 years ago. It is not stale the way news can be stale. It is just slightly, persistently delayed. When we eventually get there, if we ever do, we will be arriving in a system that is simultaneously familiar to us as a destination we've aimed at for decades and completely alien to us as a physical environment. We will be visitors in a sense so total that the word visitor doesn't quite contain it. We will be organisms designed for one star, arriving at another one, carrying everything that makes us what we are, like a seed carried on the wind, hoping the soil is right. Chapter 9. The Milky Way. The Milky Way is a barred spiral galaxy about 100,000 light-years across. Most estimates put the thickness of the galactic disk at about 1,000 light-years. The number of stars is somewhere between 200 billion and 400 billion. Our Sun sits roughly 26,000 light-years from the galactic center, about 2/3 of the way out from the core toward the edge of one of the galaxy's spiral arms. The galactic year, the time it takes for the Sun to complete one orbit around the galactic center, is about 225 to 250 million years. The Sun has completed approximately 20 of these orbits since it formed. The last time our solar system was in this exact position in the galaxy, the most complex life on Earth was simple marine invertebrates. The first fish was still 30 million years away. Traveling across the Milky Way is not something we can currently contemplate in any practical sense. At Voyager 1's speed, crossing the full 100,000 light-year width of the galaxy would take roughly 1.7 billion years. All of human civilization, all of human history, all of human existence represents about 0.000006% of that journey time. And that's at our current fastest speed, which is itself almost comically slow by cosmic standards. But let's say you could travel at the speed of light. That is impossible in the physics we understand, but as a thought experiment, at the speed of light, crossing the galaxy would take 100,000 years. Modern anatomically human humans have existed for about 300,000 years, so even at the cosmic speed limit, the crossing would take 1/3 of the entire history of our species. And in that time, generations would be born and die on the ship. Not one lifetime, not even 10 lifetimes. Hundreds of generations would live their entire existence inside the spacecraft, born into it, educated in it, growing old in it, dying in it, having never set foot on any world. The ship would be their entire universe. The children born in the 3rd generation of that journey, or the 50th, or the 100th, would have no meaningful psychological connection to the Earth that the original crew left behind. It would be a myth to them. A story told by their grandparents' grandparents' grandparents. The actual memory of solid ground, of wind, of the smell of rain would be gone within a few generations. And when those people arrived, if they arrived, they would not be going home to anything. They would simply be going somewhere new. The galactic center is the most hostile environment in the entire Milky Way. Toward the core of the galaxy, stars become so densely packed that instead of the nearest star being 4 light-years away, as it is from our Sun, the nearest stars in the galactic core are less than 1/10 of a light-year apart. the stellar density is thousands of times greater than in our neighborhood of the galaxy. The night sky from a planet in the galactic core, if such a planet exists and is not already being cooked by the proximity of so many nearby suns, would be a blaze of light without any true darkness. There would be no night. Every direction you looked would be blazing with nearby stars. And at the very center of the Milky Way sits Sagittarius, a supermassive black hole with a mass of about 4 million times that of our Sun. If our Sun were the size of a marble you'd hold in your hand, Sagittarius would be a marble 4 million times heavier. You couldn't hold it. You couldn't be anywhere near it. At the distances involved, the gravitational tidal forces around a black hole of that mass would tear apart any structure that came too close. This process, called spaghettification in the technical literature in what might be science's finest naming decision, would elongate your body along the direction of the black hole's gravitational gradient while compressing it sideways. The differential between the gravitational pull on your feet and the gravitational pull on your head would stretch you like taffy. You would not die. You would be pulled apart along the direction of the force until you were no longer recognizable as a human form. But even before you got close enough for spaghettification, the galactic center is awash in high-energy radiation from the stars, from the black hole's accretion disk, from supernovae that occur far more frequently there than in our quiet suburban arm of the galaxy. Researchers have detected enormous bubbles of high-energy plasma called Fermi bubbles, extending tens of thousands of light-years above and below the galactic plane, apparently the remnants of enormous energy releases from the galactic center in the relatively recent astronomical past. The radiation environment near the core of our galaxy would be fatal to unshielded life many times over. Chapter 10. The Local Group. The Milky Way is not alone. It is part of a gravitationally bound collection of galaxies called the Local Group, which contains somewhere between 54 and 80 galaxies, depending on how you count the smallest dwarf galaxies at the edges. The most significant members after the Milky Way itself are the Andromeda Galaxy, also known as M31, and the Triangulum Galaxy. Andromeda is the largest galaxy in the Local Group, and it is currently heading toward us. Andromeda is currently about 2.537 million light-years away. If the distance from Earth to the Moon represented 1 centimeter on a ruler, the distance to Andromeda would be about 33 kilometers. That is, the Moon's distance shrunk to a centimeter, and the Milky Way's nearest large neighbor is 33 kilometers further. And yet, in perhaps 4.5 billion years, the two galaxies will collide. Not smash together the way physical objects smash, because galaxies are mostly empty space and their stars will pass each other like thoughts passing through a mind. But gravitationally, the two will merge, tearing each other's spiral structures apart over hundreds of millions of years, eventually settling into a single large elliptical galaxy that astronomers have already informally named Milkomeda. The journey to Andromeda, at any speed our physics currently allows, is simply not a journey that can be described using human timeframes. At the speed of light, the trip takes 2.5 million years. At Voyager 1's speed, it would take roughly 44 billion years. The current age of the universe is 13.8 billion years. Traveling to Andromeda at our current fastest speed would take 3 times the age of the universe. By the time you arrived, the stars in Andromeda would have changed. Many of the ones you were aiming for would have died. New ones would have formed. The universe itself would be unrecognizably older. In intergalactic space, beyond the Milky Way, you are truly and completely alone in a way that even interstellar space does not prepare you for. In interstellar space, you are at least surrounded by other stars. The sky is full of light sources. In intergalactic space, the Milky Way itself becomes a smear of light in the sky, and the other galaxies are faint smudges visible only with instruments. The darkness between galaxies is the deepest darkness in the observable universe. The density of matter drops to near zero. The temperature of the surrounding medium is near the 2.7 Kelvin background temperature of the universe. The cosmic ray flux drops because you've moved away from the galactic sources of most of those particles. And you are alone in a void that has no landmarks, no gradations of light, nothing but the occasional photon from a distant galaxy crossing millions of light years to arrive at your eye. Chapter 11. The Observable Universe. The observable universe extends about 46.5 billion light-years from Earth in every direction. The fact that it's 46.5 billion light-years across, even though the universe is only 13.8 billion years old, is not a contradiction. It's a consequence of the expansion of space itself. When the light from the most distant galaxies we can see was emitted, those galaxies were much closer to us than they are now. In the time it took that light to travel to us, the space between us and those galaxies expanded, and now they are 46.5 billion light-years away. And because of that expansion, light from galaxies beyond a certain distance will never reach us no matter how long we wait. The universe is expanding faster than light can cross some of those distances. The total number of galaxies in the observable universe was estimated by a 2016 study to be approximately 2 trillion. 2,000 billion galaxies. If you counted one galaxy per second, it would take you over 63,000 years to count them all. You would need to start counting before the invention of writing and continue through all of recorded history and still have tens of thousands of years left to go. And each of those galaxies contains, on average, hundreds of billions of stars. The number of stars in the observable universe is estimated at roughly 10,000 billion, written as a 10 followed by 23 zeros. There are more stars in the observable universe than there are grains of sand on every beach and desert on Earth. To travel to the edge of the observable universe would require not just crossing space, but in some sense outrunning the expansion of space itself. And even if you could somehow cross that distance instantaneously, you would find yourself at a place that is no longer the edge of anything. The universe extends beyond what we can observe, in all likelihood infinitely, and the edge of our observable universe is just the boundary of the light cone, the region from which light has had time to reach us. Stand at the observable universe's edge, and your own observable universe from that new vantage point would extend 46.5 billion light-years in every direction from where you now stand, with the Milky Way as a faint smudge somewhere in it. At the edge of the observable universe, you would be in a region of space where the galaxies are moving away from you at close to the speed of light due to cosmic expansion. The light from these galaxies is redshifted so severely that it drops out of the visible spectrum entirely. You could not see them with your eyes. They would be invisible except to instruments sensitive to radio waves and microwaves. The universe would look, to your naked eyes, almost completely dark in those directions. A darkness so profound it would feel like blindness. What would kill you at the edge of the observable universe? The same things that would kill you in intergalactic space, elevated to their most extreme form. The cold is the 2.7 Kelvin background temperature, that thin remnant warmth of the Big Bang, surrounding you from all directions. The radiation is the cosmic microwave background itself, the afterglow of the universe's birth, now so cooled and stretched that it's harmless by itself. But the isolation is total. The nearest galaxy would be hundreds of millions of light-years away. The Milky Way would be so distant, its light would never reach you in your lifetime. You would be floating in a darkness so complete that the universe would feel, for the first time, genuinely empty. And in that emptiness, you would begin to understand something that we only get glimpses of from our comfortable terrestrial vantage point. The universe is not full. It is almost entirely empty. The stuff, the galaxies and stars and planets and everything made of matter and energy, represents a vanishingly thin coating on a vast structure of emptiness. We are not swimming in a universe. We are clinging to isolated rocks in an enormous void. Chapter 12. What dark energy does to you. There is something else at the edge of the observable universe, something that has no analogy in human experience and that physics only began to understand in 1998. Dark energy. We do not know what dark energy is. We know it exists because the universe is expanding and the expansion is accelerating. Something is pushing the galaxies apart faster and faster. That something, whatever it is, constitutes roughly 68% of the total energy content of the universe. Dark matter, which we also cannot see and can only infer from its gravitational effects, makes up another 27%. All the ordinary matter in the universe, everything you have ever seen, every star, every planet, every galaxy, every atom that has ever existed in any form, represents about 5% of the total content of the universe. We are made of the minority ingredient. Dark energy has a specific consequence for long-term travelers that is worth thinking about. Because the expansion of space is accelerating, the most distant galaxies are not just moving away from us, but are accelerating as they do so. In the far future, billions of years from now, the most distant galaxies will accelerate past the speed at which light can bridge the gap, and they will disappear from our observable universe forever. The night sky will gradually empty. In 100 billion years or so, a civilization in the Milky Way would look out at a sky containing only the galaxies of the local group, everything else having receded beyond the observable horizon. In trillions of years, the local group itself will have merged into a single galaxy, and beyond it, the night sky will be perfectly, permanently, cosmically dark. Future civilizations, if any exist by then, will have no way of knowing from direct observation that the universe contains anything beyond their own galaxy. They will have been born into the darkness, and they will have no evidence the rest of the universe ever existed. What does dark energy do to you, physically, right now? Nothing detectable. On the scale of human bodies, or even of solar systems, or even of galaxies, dark energy is far too weak to matter. It only dominates at the largest scales of the universe, where it is slowly but relentlessly pushing structures apart. But understanding that dark energy exists, and that it constitutes more than 2/3 of everything, and that we have almost no idea what it actually is, tells you something important about the state of human knowledge. We have mapped the universe to extraordinary precision. We have measured the temperature of the cosmic microwave background to 4 decimal places. We have detected gravitational waves, ripples in the fabric of space-time, from black holes merging billions of light years away. And we still don't know what 95% of the universe is made of. We have described the universe's content with beautiful mathematics and found that most of it is labeled unknown. Chapter 13, the answer to the question. So, how far could you travel in space before you die? Let's come back to Earth for a moment and think clearly about this. The real answer depends on the meaning you assign to the word travel. If travel means unassisted, with no technology, then you die the moment you leave the atmosphere. The vacuum causes your blood to vaporize and your lungs to rupture in under a minute. But that's not an interesting answer. If travel means with the best spacesuit technology we currently possess and nothing else, you die within days or weeks from radiation exposure depending on solar activity and where you are. You might survive a trip to the moon's surface. You might not make it back. If travel means with the best spacecraft technology currently operational, including life support, radiation shielding and everything aboard the International Space Station, you can survive for months, possibly up to a year. Beyond that, the cumulative radiation dose, the bone density loss, the vision problems, and the cardiovascular changes begin to impose limits that we cannot currently overcome. The record for continuous time in space is held by cosmonaut Valery Polyakov, who spent 437 days, just over 14 months, aboard the Russian Mir space station in the mid-1990s. He was in Earth orbit within Earth's protective magnetic field, which provided some shielding that deep space does not. He walked off the spacecraft after landing but required significant recovery time. 14 months is roughly the outer boundary of what current technology permits. If travel means with technology we can envision but haven't built yet, then you might survive a Mars mission, might survive some years in interplanetary space with excellent shielding, but the interstellar distances remain utterly beyond any solution we can currently propose. The fundamental problem of radiation in interstellar space, combined with the timescales involved, makes the trip to even the nearest star biologically fatal under current physics as we understand it. Unless you could travel so fast, close enough to the speed of light, that relativistic time dilation compressed decades of ship time into something manageable. But that requires energies we cannot currently produce at anything like the scale needed. And if travel means indefinitely, forever, with any technology, well, the ultimate answer involves the universe itself. In the very far future, as stars burn out and black holes evaporate through Hawking radiation over timescales so long that the number of zeros required to write them would fill this entire script, the universe arrives at a state called the heat death. A condition of maximum entropy in which every energy gradient has been equalized, no work can be done, no biological or mechanical processes can occur, no order can be maintained. It is the final destination. It is where everything, every atom in your body, every memory encoded in neural pathways, every piece of art ever made, every word ever spoken, ultimately arrives. The last possible barrier the universe imposes on travel is not space but time, not distance but entropy. Chapter 14. The strange comfort of all this. There is something I want to say here, something that has been building across everything we've walked through together, and I want to try to say it carefully because it's easy to get wrong. The universe is not hostile to us. It's indifferent. And indifference is different from hostility in a way that matters. Hostility implies an adversary. It implies intent. And the universe has no intent. It has physics, and physics is the same everywhere in the observable universe. The equations that describe how hydrogen atoms combine to form stars, the equations that describe the expansion of space, the equations that describe the decay of radioactive nuclei, they are the same equations in every galaxy, in every era, at every scale. We are not being excluded from the universe. We are simply and for now too fragile for it. But here is the thing about fragile. Fragile things can change. Life on Earth started as single-celled organisms that could not survive in oxygen, and now here we are breathing it. The universe is 13.8 billion years old. We've been doing anything resembling science for a few centuries. We've been in space for decades. We are, in cosmological terms, newborns who have only just started to open our eyes. The fact that interstellar travel is currently beyond us is not the same as the fact that interstellar travel is permanently beyond us. It is a fact about where we are in our development, not about where we might go. And there is this too. Every atom in your body is connected to the places we've talked about today. The iron in your blood was forged in the core of a massive star that exploded before our sun formed. The calcium in your teeth was scattered through space by a supernova. The hydrogen in the water that makes up 70% of your body is among the oldest material in the universe, formed in the first 3 minutes after the Big Bang, floating through the cosmos for 13.8 billion years before it ended up in you. You are not a visitor to the universe. You are made of it. The universe, in some literal sense, is not looking at you from the outside. It is looking at itself through you. You are the universe's way of being curious about its own nature. The distances we've talked about, the radiation, the cold, the impossibility of the timescales, all of that is real. And it is also a measure of how much there is. A universe that could be crossed in an afternoon would be a smaller thing than what we have. The sheer scale of it, the thing that would kill us at every stage of the journey, is also the source of every light in the sky. The same forces that make deep space deadly are the forces that made the stars, and the stars made us. The fire that would kill you in minutes of exposure is the same fire that cooked the carbon you're made of. There is no contradiction there, just consequence. Chapter 15, The Biology of the Impossible. Let's come back to the body one more time, because the body is where all of this is most real. Not in the abstract cosmic distances or the equations of radiation physics, but in the specific details of what human flesh does and does not tolerate. The human cardiovascular system is a beautiful piece of engineering that spent 4 billion years being refined by evolution, and it was refined for exactly one set of conditions. One gravity, one atmospheric pressure, one magnetic field, one set of radiation levels, one rhythm of light and dark. Change any one of these parameters significantly, and the system starts to fail in specific, predictable, documented ways. Change all of them simultaneously, and the failure modes cascade. In long-duration space travel, cardiovascular changes begin within the first few days. Without gravity, the heart doesn't have to pump blood upward against a full gravity gradient, and it gradually becomes smaller and less powerful. Blood shifts toward the head and torso and away from the legs. The legs become thinner over time, visibly, in a way that astronauts notice and document. The face becomes puffy from the excess fluid. Astronauts have described the sensation as like having a head cold that never goes away, a constant mild pressure in the sinuses and behind the eyes. The immune system is also affected by spaceflight in ways that are still being studied. Latent viruses, herpes viruses that the immune system normally keeps suppressed, reactivate in space. Astronauts shed active herpes virus in their saliva and urine during and after space missions at rates much higher than on Earth. The immune system is suppressed by the combination of radiation, stress, sleep disruption, and the general physiological chaos of living in an environment the body was never designed for. On a short mission, this is manageable. On a multi-year interstellar journey, an immune system that is persistently compromised would be enormously dangerous, because infections that would be trivial on Earth could become life-threatening without adequate immune response. The gut microbiome, that ecosystem of trillions of bacteria that lives in your digestive system, and which is increasingly understood to influence everything from metabolism to mood to cognitive function, is also altered in space. The microbial communities shift in composition in ways that are not fully understood, but that may contribute to many of the health effects observed in astronauts. A long-duration space crew would be essentially cut off from the diverse microbial exposure that keeps terrestrial microbiomes healthy and balanced. They would be living in a closed environment with a small group of people, breathing recycled air, eating processed food, and their gut bacteria would reflect that. The psychological effects deserve their own careful attention. Research on isolated and confined environments, from Antarctic winter overstations to submarine deployments to the Mars 500 simulation study, where 6 volunteers spent 520 days in a sealed habitat to simulate a Mars mission, consistently identifies specific psychological phenomena, monotony and tedium, which sound minor but which can be genuinely debilitating over months. Interpersonal conflict within the crew, which in a confined space with no escape, has the potential to be much more serious than the same conflict in a normal setting. Asthenia, a condition of persistent fatigue, apathy, and reduced motivation, which is well documented in long-duration missions. Communication delays, which as distances grow increase from minutes to hours to something that eventually makes real-time communication impossible. And a phenomenon the researchers call third-quarter phenomenon, a specific dip in morale and performance that occurs roughly 3/4 of the way through a mission, when the end is in sight but still far enough away that motivation sags. On an interstellar mission lasting decades, there would be no 3/4 point. Not in any meaningful sense. There would be generations of 3/4 points. People would be born and grow old and die before the mission ended. And those people, the ones born into the journey, would never know a different life. The question of whether such a life constitutes a good life, a full life, a life with the full range of human experience, is not one that science can answer. It is a philosophical question that the people living that life would have to answer for themselves. Chapter 16. The machines that go where we cannot. We should pause and acknowledge something. While a human body cannot survive in most of the environments we've discussed today, machines can. Our machines have been to places that are completely fatal to human biology, and they have been there for years. Voyager 1 and Voyager 2, launched in 1977, are still operating in interstellar space. Voyager 1 is the most distant human-made object, more than 23 billion kilometers from the Sun, and still sending back data. The signal it transmits, moving at the speed of light, takes over 22 hours to reach Earth. It carries a golden record, a disk of sounds and images chosen to represent life on Earth, sealed in a gold-plated copper case with instructions for playing it. There is something quietly beautiful about the fact that we sent our music and our voices and recordings of wind and surf and human heartbeats into interstellar space on a machine, on the off chance that something out there might find it and understand it. It is the longest message in a bottle that has ever been sent. And it is currently somewhere out there in the dark between the stars, carrying the sounds of rain and children laughing and greetings in 55 languages. The New Horizons spacecraft, launched in 2006, flew past Pluto in 2015 and is now heading toward the outer reaches of the Kuiper Belt, currently about 8.5 billion kilometers from the Sun. The Parker Solar Probe has been diving into the outer atmosphere of the Sun itself, surviving temperatures of over 1 million degrees in the corona by using an extraordinarily effective heat shield, getting closer to the Sun than any human-made object ever has. The James Webb Space Telescope, launched in December of 2021, sits at a gravitationally stable point 1.5 million kilometers from Earth and has already returned images of galaxies from the earliest epochs of the universe, light that traveled 13 billion years to reach its mirrors. These machines go where we cannot. They are our extended nervous system, our disembodied senses, our way of seeing and measuring and touching the universe without the fragility of biology. They are the first step in something that may, eventually, be the answer to the question we started with. Not how far a human body can travel, but how far human curiosity can reach. And that, so far, appears to have no limit. Chapter 17. The question nobody asks. There is a version of this question that almost nobody asks, and it might be the most important one. Not how far you could travel before you die, but how far you could travel and still come back. And that turns out to be the harder question, because the universe in all its vast indifference does not particularly care about the return journey. The mathematics of getting home are more brutal than the mathematics of getting there. To travel to a distant destination and return, you need not just the energy for the outward trip, but for the deceleration, the turnaround, the re-acceleration, and the inward journey. For a rocket-powered spacecraft, the fuel requirements scale exponentially with the velocity you want to reach. This relationship, described by the Tsiolkovsky rocket equation, means that getting to 10% of the speed of light and coming back would require a spacecraft that is mostly fuel-to-payload ratios that dwarf anything we have ever built. The mass of fuel required would be comparable to the mass of a small moon for the velocities we're talking about. And fuel is dead weight on the return trip. This is why some serious researchers have suggested that the first interstellar missions, if they happen, will be one-way. Not because the planners are careless with human life, but because the one-way option is a genuine one in a way that other difficult journeys are not. Columbus didn't plan to stay in the New World permanently. But the first humans who leave the solar system for the stars may, from the very beginning, be leaving without any expectation of return. They would be colonists in the truest sense. They would be founding something, not visiting something. And that changes everything about what the journey means. What does it mean to leave and never come back? Humans have done it before. The ancestors of the people who first populated the Pacific Islands left their home islands in canoes and sailed for thousands of kilometers into open ocean with no way of knowing what was on the other side. Some of them didn't make it. Some of them found new islands and stayed because there was no practical way back. They were not stranded. They were arrived. They were home. And their descendants, tens of generations later, made those islands into civilizations. The interstellar version of that story would be almost incomprehensibly scaled up, but the human element, the willingness to go somewhere from which there is no return, is not new. It is as old as human movement across the surface of this world. Chapter 18: What the Light Remembers. There is one last thought I want to share before we land this journey somewhere solid. It has to do with light. Every time you look at a star, you are looking into the past. The light from the nearest star, Proxima Centauri, left its source 4.24 years ago. You are seeing it as it was in the recent past. The light from Andromeda left that galaxy 2.5 million years ago. When Andromeda's photons arrive at your eyes, they carry information about a galaxy as it existed when the ancestors of modern humans were just beginning to make stone tools in Africa. The most distant galaxies visible to the James Webb Space Telescope sent their light to us 13.4 billion years ago. Those galaxies no longer look the way they did in those images. They have evolved and changed, and in many cases their stars have been born and died and born again many times over in the time it took their light to reach us. We are looking at memory. The universe's memory, stored in light, traveling at the maximum speed that physics allows. Here is the thing about that. When you look at the night sky, everything you see has already happened. You are surrounded by the past. The present of those stars, what they look like right now, is inaccessible to you. You are receiving messages from history. And when you die, eventually, the light from your existence, the photons scattered by your life, will continue traveling outward into space at 299,792 kilometers per second. They will reach the moon in just over a second. They will reach the sun in 8 minutes. They will reach Jupiter in about 40 minutes. They will reach the nearest star in 4.24 years. And they will keep going, diluting, spreading, weakening, but going. Long after every person who knew you has themselves become starlight, some small record of the light of your existence will still be traveling outward, out past the asteroid belt and the outer planets and the heliopause, out into the space between stars, a vanishingly faint signal heading into the dark. You will never travel to the edge of the observable universe. Neither will I. Neither will anyone alive today, or any generation we can currently envision. But our light is already going there. The photons that have bounced off you as you sat reading these words are already on their way. We cannot travel as far as the universe extends, but we have already sent our signal out into it. And isn't that something? So here is the payoff. Here is what this journey was actually about. The question of how far you could travel in space before you die is really a question about what it means to be human in a universe that didn't build itself around us. And the answer is, not very far. On cosmic terms, barely a hair's width from where we started. Even the nearest star, which at the speed of light would take only 4 years to reach, is an insurmountable destination given our current technology and biology. We are, in the grandest possible sense, local creatures. Our biology evolved here, our psychology was shaped here, our chemistry depends on conditions that exist on this specific rock, orbiting this specific star in this specific galaxy. We are, in the deepest biological sense, Earthlings. And that is not a failure. It is a specificity. It is the same kind of specificity that makes every organism extraordinary. But here is the thing about us that is different from every other organism that has ever existed on this planet. We know what's out there. The deer in the forest does not know that there are other continents. The fish in the ocean does not know that other oceans exist. But we, right now, with our telescopes and our mathematics and our robotic scouts in the dark, we know about the Andromeda Galaxy. We know about the galactic center. We know about the heliopause and the cosmic microwave background and the distribution of dark energy through the large-scale structure of the universe. We cannot go there, but we know it's there. And that knowing, that reaching out with the mind into distances the body cannot cross, is perhaps the most distinctly human thing about us. We are the universe looking at itself with awareness. We are the part of it that asks what it is. And that asking, even when the distances defeat us, is itself a kind of traveling. Every piece of knowledge we have about the universe, every measurement, every equation, every image from a telescope, is in some sense a journey we've taken without leaving. We've sent our curiosity to places our bodies cannot follow. And in that limited but real way, we have already crossed the galaxy. We have already seen the edge of the observable universe. We have already, through our instruments and our mathematics, put our minds where our bodies could never go. The universe is 13.8 billion years old, and we've been here for the blink of an eye at its very end. We have learned almost nothing in the grand scheme of what there is to know. And yet we have learned that the universe is 13.8 billion years old. We have learned its composition, its age, its expansion rate, its likely fate. We have listened to it and mapped it and understood, at least in part, why it is the way it is. That is not nothing. That is a small miracle hiding inside an ordinary Tuesday on an unremarkable blue rock. The journey we've taken today, from the Moon to Mars to Jupiter to the outer solar system to the nearest stars and across the galaxy and through the local group to the edge of what can be observed, is not a journey about death. Despite everything that would kill you at each stage, despite the radiation and the cold and the vacuum and the loneliness and the timescales, the journey is about the distance between what we are and what we dream. And that distance is real, and it is enormous, and it will not close easily or quickly. But it is not fixed. Nothing about us has ever been fixed. We went from the first tentative steps of Homo sapiens on the African savanna to walking on the moon in 300,000 years. In cosmic time, that is not even a sentence. It is a syllable. The story is barely beginning. And there is a new dilemma at the bottom of all this. A question that this journey raises that we haven't answered and may not answer for a very long time. If the distances are this vast, and the timescales this long, and the universe contains 2 trillion galaxies each with hundreds of billions of stars, then the question of whether other life exists somewhere in all of that is no longer an abstract philosophical one. It becomes statistical. It becomes almost certain. And if life exists elsewhere, if somewhere in those 2 trillion galaxies something has developed biology and curiosity, and the same ache we feel looking at a clear night sky, then the same distances that make the universe so dangerous to travel are also what separates us from them. They are out there, and they cannot reach us, and we cannot reach them, and we are communicating through the same medium, the same photons scattered into space, the same signal heading outward at the speed of light. We are calling to each other across a distance that may never be crossed. And neither side knows whether the other is listening. That is one of the questions scientists are working on right now. That is the one that keeps people in observatories awake at night, scanning, listening, looking. And if you find that as compelling as I do, the video I want you to watch next is right here, and it goes somewhere this one didn't dare.